So yes, today I will speak about some R&D work that has been going on in the accelerator and parallelization areas. Okay, so historically, the CPU has been the computational resource that has been mostly used in HAP. But high-performance computing facilities now offer a lot of new things, like cluster of hundreds or thousands of CPUs, sockets and NUMA nodes with different interconnectivity to answer different demands, heterogeneous resources like CPUs and GPUs, low energy consumption resources like FPGAs, and containers and frameworks which make use of the hardware topology to ensure an efficient level of resource allocation and resource usage. This means that different levels of parallelization are now achievable. If we look at the hardware parallelization levels, the most low-level one is from the instruction level. So the CPU has now built-in instruction pipelines to speed up the execution. There's also the thread-level parallelization, but also the process level, which involve the parallelization within the same node or within different nodes of the same cluster. There's also the offloading of some part of the computation to the accelerator, and this is with the relation of the CPU with the GPU. If you look at the software parallelism, we look at two different procedures, like data parallelism, which means the same code is executed on different data, and task parallelism, which means that each thread or process executes a different part of the code on the same or on different data. And the most used data parallelism approaches are vectorization and multithreading. And now, if we look at the ACTS track reconstruction, there are two different main steps. So the first one is the seed finding, which is a combinatorial search in space. And the second one is the track following, which is the combinatorial Kalman filter for simultaneous track finding and fitting. Since this part covers the integration of the equation of motion of charged particles in a magnetic field and the propagation of the track parameters and the covariance matrix through the detector's geometry, we can all imagine that this is compute-intensive algorithms. But ACTS offers the optimal environment to explore all the level of parallelism and the strategies that we explored on the previous slide. So the seed finding, for run 2, 20% of the total reconstruction time was spent on seed finding, and an estimate of 50% is for the 200 pileup. Now, the computational characteristics of the seed finding are the fact that it's a combinatorial problem and the fact that the problem space can be easily decomposed in sub-independent spaces which can be explored in parallel. This makes the seed finding a perfect candidate for massive parallelism. Recent ACTS research explored CPU thread-level parallelization and GPU-accelerated support using both Cycle and CUDA. With respect to the CPU parallelism, OpenMP was used for thread-level parallelism, and the results showed a very good speedup. The GPU-accelerated side had two different projects. So the Cycle implementation showed very good results. The CPU and the GPU results matched 100% and show great scalability when working with space point as arrays. As right now, they are iterators, and there is a conversion time needed from converting them from iterators to array, which makes the total execution time a bit worse. The CUDA implementation proves great scalability and efficiency. The CPU and the GPU results matched 100% for the number of space points, which is smaller than 200,000, which is a relevant number for the next high luminosity estimates. What you can see in the table is the validation results. So the number of seeds that were produced by the CUDA code and the number of seeds produced by the CPU code is identical. And the seed matching rate ratio is almost 100%. And the small differences that you see here are due to the rounding precision of the CUDA compiler. Since the results of this code are very good, it is in progress of promoting from experimental to production ready. If we look at the track finding and fitting part of the code, the ACTS examples already use task-level parallelism through Intel TBB library support. Also, imbricated task parallelism and GPU offloading were explored. So for the multi-threaded implementation, which comes on top of the existing multi-thread solution, this showed very good speed up and a reduced memory footprint. It also uses TBB for the task parallelism, similar to the event handling. The GPU accelerated solution uses CUDA, and at the moment, the adaptive fourth order Runge-Kutta-Nystrom method was ported to CUDA, and the results at the moment are comparable to the ones obtained with the CPU implementation using OpenMP. The ongoing efforts are in many directions. So one of them would be to port the full functionality of the Kalman filter on CUDA and then measure the full performance. The other direction would be to explore parallel numerical algorithm with the goal to speed up the integration. And the last one would be to investigate the hardware awareness and how that could help us optimize the parallelization. So as a summary, we looked at the motivation for exploring parallel architectures, and this lies in the need of efficiently making use of the computational clusters. I've showed you a few examples of some R&D work based on OpenMP, Cycle, and CUDA for the seed finding, and based on TBB and CUDA for the track fitting. Also, on the last slide, I've summarized a few of the ongoing research that have been currently going on. And that's it. Thank you.
Thanks, Georgiana. Any questions? Andy, you're typing something. Do you want to just speak up?
Right. Yes. So for the discussion on having if you want to sustain the full Kalman filter as we have it right now on the GPU, I think we will have to think about having a different view of the geometry model. So it's part of my prepared contribution for the discussion on Tuesday and Thursday will be, first of all, the streamlining, end of the streamlining work package for the geometry, and then we could try to discuss whether there is a better way than a polymorphic geometry description for the GPU. But then we also should understand whether we're not diverting too much into different detector descriptions for a GPU and CPU, and therefore don't sustain close compatibility of the code.
Okay, other questions? I had maybe one on the seed finding that you showed. I didn't manage to look at all the results you were showing carefully enough. Are we able to drive any comparisons between the different platforms that we've been testing out, or is it still too early to try and see which ones seem to be the most appropriate?
So the seed finding, I think the most promising results are based on the CUDA implementation. And here is in the chart presented on this slide, maybe I can show it a bit. So on this slide, we have the time, the speed up time. So the speed up time, which is practically the time of the serial execution of the CPU divided by the time for the CUDA implementation. So in the time frame of the number of spaces between 50,000 and 100,000, which I think is relevant for high luminosity, we can see a speed up of 15. So the code on the CUDA platform, it's 15 times faster than the CPU implementation. I think this is the most advanced result at the moment. Maybe Andy, you can correct me if I'm wrong.
Oh, that's pretty much summarized. I have not in my head now whether this also includes the mem copy onto the GPU, but I think so.
I think
that
so
was
too.
Actually going to be my question, is if this is just the execution time or really the full time?
I think it's the full time execution.
Wow, that's pretty impressive then.
Yes.
And I guess this is compared to a single threaded CPU execution, right?
I don't know how to answer that.
Yes, I think so.
Yeah, I mean, you always need to compare it to the full processor. because the price for one of these GPUs is similar to the processors.
Yeah, I think I completely agree. I think from our project point of view, we will follow as soon as there are guidelines, digestible guidelines. I don't know who comes up with that, HSF, whoever, to show that. I think that would be the best thing to do. At the moment, it's nice to show this, but one really needs to say what is shown here. Yeah, so we probably just need to specify on the slide whether this is single processor. Yeah, and then how much ping for bucks this is another story, of course. Yeah.
I guess my main point was not that this would not be good. I think in most cases, well, at least in PotaTrack, people try to do as much on the GPU as possible. And at that point, the question becomes not so much how much faster one specific task is on a GPU compared to a single thread on the CPU, but if you can do 90% of your tracking on a GPU, then even it just becoming a little bit faster can be a big win, because you then 90% of it runs there. You don't have to copy stuff back and forth.
Attila, for completing the GPU implementation, that would mean on top of the CEDA, the combinatorial track finder with FITA implemented, if this goes in one go, would be ideal. And for this, we need to have the propagation and the geometry. And as Georgiana has shown, there's some first R&D. So at least the pure propagation without complicated geometry runs is not too difficult to port. There's a few things which we have certainly not done with GPU in mind in the implementation, but that's something to learn from. Xiaokong, you can probably better comment on that if you want.
Yeah, so so this is currently just for the stepper. So we have basically managed to put the stepper on the GPU, but not anything with the geometry or the track parameter or the measurements, or even finally the common feature. So we don't have that yet. So this is pretty much just R&D to see if this works with the GPU.
Right, but just to clarify, I'm really not trying to be negative here. That was not why I was commenting. I guess my comment was just that even if one could say that, well, if all that we would ever do on a GPU is the seed finding, then yeah, splitting it up by a factor of 15, that by itself doesn't mean a whole lot. The hope here is, and I guess everybody's hope is that more and more could be pushed off to the GPU, and then we can hope for something actually meaningful. So I'm all positive about all of this, just to be clear.
Thanks, Attila. Other questions or comments?